except me. It's always difficult to be the last speaker on the last day. But anyway, thank you for the local organizers, Aldo and Peter, and all the guys, Julian, and Jack's been tremendous. Where's Jack? Everybody. So thank you very much. Also, so I'll be talking about a different approach to modified gravity. Okay? So there's been many talks about modified gravity over the week, but basically focusing on the metric formalism. So this is a different approach which unites and combines the metric formalism and the Palatini formalism. So it's got some very nice and interesting properties that don't appear in the pure FFR metric and the pure FFR R3. So, okay. I won't go much into the considerations, but I'll just speak a bit of the need for new gravitational physics that go beyond GR and modified gravity. Okay. And I'll speak a bit about the astrophysical and cosmological implications of the hybrid theory, the gravity propagator, and I put in a new section on dark matter due to, this is the bit Martha's fault. Where's the bit? Oh, yeah. Because of dark matter. So we spoke a bit about this, so this wasn't supposed to be there. I changed a bit the talk last night, so it's just to see how you can mimic dark matter with modified gravity in the context of a hybrid theory. Okay, so I'll go into the virial theorem. Very, very brief, nothing too complicated. And if you have questions, you can talk afterwards. Okay, and also some future research, because it's still novel. There's still a lot of aspects that need to be addressed. Okay. All right. So this was spoken on Wednesday, but I'll just go through really fast. So GR is facing so many challenges, right? Okay, so first of all, difficulty in explaining specific observations, like the late-time cosmic acceleration, right? It's incompatible with also other well-established theories, quantum mechanics. There's also a lack of uniqueness. So many theories, as you've seen, that predict the exact same thing as GR and go beyond also. So the question is this indicative of a need for new gravitational physics? That was the aim of the discussion that David convened on Wednesday. So, the motivations, of course. So, a promising approach is that assume that at large scales, GR breaks down due to the late-time cosmic acceleration, and in more general action describes the gravitational field. So you can play around with this. I mean, you've seen some variants over the week, especially with R squared, the Rubinsky thing. If you want to have strong curvatures, this is the thing to do. If you're interested in the late-time cosmic acceleration, it's 1 over R, low curvatures, that term dominates, so it's there. And you can play around with this, okay? You can build as many invariants as you want. The contraction with the Ricci, the Riemann, some people talk about the vial, so there's a whole game. And as we mentioned also on Wednesday, there's too many theories, okay? So there's just too many theories. And the question is, what guides you in building these theories, okay? Is it just brute force? Is it just because you like a theory and you just confronted with local tests, the late-time cosmic acceleration, build cosmological solutions, you know? So in fact, there's no guiding principle yet, and that's really lacking. The talk by Surkey, he also gave different theories. So, I mean, in fact, and it's quite worrisome, okay? All right, so, and in fact, one can also say that the physical motivations for these modifications is that of a possibility of a more realistic representation of the gravitational fields near curvature singularities. We heard the talk by Mariam and Diego on, well, yesterday, in fact, about the curvature singularities, and also to create some first-order approximation to the quantum theory of gravitational fields. So one can do that, all right? Okay, so FFR, just very brief. It's very simple, okay, and it's got some appealing features. So it combines mathematical simplicity with a fair amount of generality, right? We see that there's a Ricci scale is a dynamical degree of freedom, as you can see from the trace equation of the gravitational field equation, right? And it also introduces a light scalar field degree of freedom, right? This can be worrisome. Okay, so it does reduce the late-time cosmic acceleration, it's a long-range field, so great. But the light scalar field strongly violates the solar system tests, as we saw Mr. V's talk and also Jose Calderon. And the way out, as they mentioned, is through the so-called Kabili mechanism. Okay, so the scalar field becomes massive with a high-density local field. Okay, and I'll just provoke the reader and just say, I mean, this is really highly contrived, right? These three mechanisms, because it's almost as if anything goes, right? So it's no problem because one can hide it away. I know it's not like that, of course, but it's almost like that, you know. So one can say, I mean, can these screening mechanisms be evaded? So, and when we started working with the hybrid theory, we saw that they could, and that was really, how do you say, interesting. You know? So that motivated us to go further, right? So just for a brief introduction, so you have basically three approaches to FFR. You have the metric formalism, where the fundamental field is the metric. Okay, there's the Palatini formalism, where the fundamental field is the connection. So it's not the Liouvita. It's the Liouvita of an auxiliary metric, which can be taken back to the physical metric, which is the one that matter is coupled to. You can also take into account the metric-affine formalism, which now matter is also coupled to the connection, not only the metric. I would say there's a fourth approach, which you combine the metric and the Palatini approaches together. And this brings in some very, very interesting results, which you will see in a moment. Okay, okay, so the action. So GR is fine, right? So we just add something there that's extra, that tries to explain what GR doesn't explain, right? So the R here is the Einstein-Hilbert term constructed through the metric. So we can call it the metric curvature. And then we construct a new term, okay, where this curly R is the Palatini curvature. So it's defined in terms of a new connection, okay? It's not the Liouvita connection of the physical metric, okay? It's the Liouvita of a new auxiliary metric, okay? So one can play around with this now. You can find the field equations, you vary the action with the metric, you get the gravitational field equation. You vary the action with the connection and you get the evolution equation for the connection, okay? And you can solve this thing and you can find the relationship between the physical metric that appears here. I won't do this because it's quite trivial, but it's conformally related to the auxiliary metric, okay? So you can think of it as a biometric theory. It's independent of those biometric bigravity theories that's all very common in the literature, but it can be thought of as a biometric. One has a physical metric, which is the one that matter is coupled to, and then you have this auxiliary metric, okay, that's defined through this new term. Okay. So that's the starting point. All right, so I'll be following this paper. It's this review paper that came out last year, and one can work with the curvature with the geometric approach. Okay, it's very messy. So it's much easier if you go to a scalar tensor representation. So people who work on this will say, oh, that's very similar to something I know. Very similar to the Palatini formalism represented in the scalar tensor representation, right? Because okay, so the metric f of r, if you go to a Brown-Sticky, it's equivalent to a Brown-Sticky theory when the Brown-Sticky perimeter is equal to 0. Okay? The Palatini, when you go to the Brown-Sticky theory, it's when this omega Brown-Sticky perimeter is equal to -3/2, where now the scalar field is coupled to the curvature. Here it's very similar, but the coupling with curvature to the scalar field is different. So we have this extra term here. Okay? So this makes all the difference. This simple coupling makes all the difference. Okay, if you prefer to work in the Einstein frame, and you take into account the fifth force that David spoke on yesterday. You can go into the Einstein frame, you just do a conformal transformation that takes you to this Einstein frame Lagrangian, and you can redefine the field and take it into a canonical form. So if you prefer working in the Brown-Sticky frame, okay, it's fine. If you want to go to the Einstein frame, just do this transformation and do all the stuff you do. Okay, now going into the weak field and slow motion regime. So we find that the Raman perimeter, that the BPM, the post-Newtonian perimeter, is given by equation 7. So you see, I mean, it's a very simple exercise. I mean, how do you make that to be 1? Okay, so there's different approaches, right? With the pure f of r metric, you say that you have a very large mass okay, short range, the so-called immediate effect, and this here, okay, so gamma is 1, right? But there's a different mechanism, okay? So contrary to the f of r metric approach, you have a different mechanism to take it to 1, which is the background scalar field is very small. So when you do this approach, you perturb the scalar field around the background, and the background value for the scalar field is very, very small. So independent of the mass of your scalar field, it can be small, okay? If that is very small, it takes it to gamma is equal to 1, okay? So you can evade these so-called screening mechanisms. They're still there, I mean, but one can evade them. One can evade this so-called PBD mechanism. I think this is really important, okay? So if you find, if you the devil's advocate would say, oh, these screen mechanisms are really highly contrived, here's an approach to evade the so-called PBD mechanism. So to give you an idea, okay, well, that's what I just mentioned. So it's, well, it's the G effective and G, gamma is equal to 1, regardless of the value of the effective mass. So just to see in f of r. Okay, f of r, that's...
So how is it different from the symmetron?
Sorry?
How is it different from the symmetron?
Just remind me what the symmetron is. Just
It's essentially the same.
oh, that's...
The Latin expectation value that gives you the coupling constant matter.
Yeah.
So in the power system this is 0, and that's why you have...
I see. Okay, you're right. Okay. But it does evade the mean, right?
Yes.
Yeah, okay. So, yeah, but you're right. That's interesting. Okay, you're right. Yeah, we can talk about it after this. Okay, but so it doesn't evade the symmetron, but it does evade the mean, right? Okay, but anyway, but it's just to tell you that's how it's distinguished between the pure f of r, right? But thank you anyway, Jose is always telling his comments. I've also added a new section because of you. Okay, so if you want to go into cosmology and in the late time cosmic acceleration, you consider a flat space-time. Yes, the modified Newton equations to give you an idea of what they look like, the scalar field, the evolution equation for the scalar field. And now for a very simple model, consider a quadratic potential. Okay, so given my equation 14, so the trace equation, okay, implies this. And due to cosmic expansion, the trace of the ingenuous intensity goes to 0, and the space-time naturally evolves into a de Sitter phase. Okay, so it's consistent with observations, right? Okay, so if V1 is positive, you have the de Sitter regime is the minimum of the potential, and the effective mass is given by this. Okay, and it's positive if you have this condition. Okay. Now, if V1 is much greater than V0, you see that the amplitude is small enough to pass the local test. Okay, that's what we want. So the exact solution is compatible with the dynamics of the scalar field in this model. Very simple model. Some more complicated models were built, but this is a very simple model to give you the idea that things are consistent with local scales and large scales. Okay, if you want to go into the cosmological dynamics, I mean, here's the expert, Sante. He's given us talk on Tuesday. And you can speak with him if you have any questions. So you can just go through a dynamical system analysis. You can define these variables, okay? And you have the feeding equation written as this constraint. Here's the autonomous system of equations, okay? And now you can build solutions, okay? If you want to construct a viable model, the potential should be such that two requirements are made. First of all, the matter dominated fixed point should be a saddle point. The de Sitter should be an attractor, so that we naturally obtain a transition to acceleration through the standard cosmological evolution. And we also want a sufficiently small value for the scalar field. Okay, so it's a paper with Sante that was done last year, not working with the statement representation, but working in a more in the geometric representation where you define a new variable in x, which is defined as the difference, the deviation from GR, and then you play around with that. It's much more complicated, but Santi did a great job. So if you want to know more, here's the paper. Okay, so cosmological perturbations for the bit. So if you want to understand cosmological structure formation, Okay? You play around with this. Consider the Newtonian gauge. You have two gravitation potentials. This is really standard, the volume potentials. And as a matter source, we consider a perfect fluid with a background equation of state omega, and the density perturbation, pressure perturbation, and the velocity perturbation. So we can show that the volume potentials are given by this relation, given by equation 18. Right? Assuming a perfect fluid, which we did, the continuity and the Euler equations are given by these relationships, and the linear part of the Klein-Bode equation is given by equation 21. Now you can consider several evolutions. Okay, if you want to take into account the method of the cosmology, the structure formation. Okay, consider this. Okay, so you take into account the quasi-static observation and the evolution equation for the equations given by equation 22. So it gives you a very nice simple approximation to track the growth of structure. We haven't done this; it's still work in progress, but we have here all the equations already working out. Okay. We can also construct this, constrain this with confusion experiments, forecasts from the vacuum fluctuations are also very important for a consistent check on the theory. Okay, so you choose vacuum, you define this curvature perturbation in this uniform field gauge given by equation 24. You obtain the linear evolution equation. Okay, so this is very useful to study inflation, right? There's also work in progress. You can also go to the Einstein frame and do the same stuff that is usually done. Okay, and you can play around with this. Okay, so the hybrid theory of space is large. Okay, because now we have an extra building block. So we have a metric, and now we have an independent connection, right? So you can just consider several terms. Consider the standard contraction of the Palatini curvature, which is done. Diego Rivera was here 2 weeks ago. He gave a nice course on this, so you must know. You can consider a hybrid contraction, okay, through the metric and the Palatini, and you can play around with this. Okay, so there's a huge building block here that's really unexplored. All right, and it's interesting to note that this theory that we're considering is stable, right? The one that's so that's very nice. Okay. Now the part that's due to Jose Butler, he told me something very simple in Lisbon, and I was thinking about it, and he's absolutely right. He's usually right, not all the time, but usually. Okay, so let's consider a more complicated theory. Okay, now for you, all right? So you have the f of r, okay, the curvature in the metric, and you have the hybrid contraction of the regime. That will give you extra modes, which you already see. Okay. All right, so playing around with the metrical equation is quite complicated. You solve the evolution equation for the independent connection, and you find the solution. Okay, I won't go into that. But the important thing is to find the graviton propagator. All right, so you consider perturbations around Minkowski space, and you infer the linearized equations for the physical metric. Okay, this provides you the graviton propagators and the additional degrees of freedom that arise. So you have this equation, which gives you a propagator, and this tail is the linearized stress energy source, right? Okay, so in the formalism of the spin projector operator, this result can be given in Fourier space in terms of two functions, A and C, which I'll show you in a while how to find in this more general theory, right? So we see already that this propagator picks up a spin 2 mode and also a scalar mode, right? That's what you want to give you the massive and probably the ghosts thing, okay? All right, so the functions A and C, to give you an idea how this works, because we'll use them. A and C is defined in terms of these complicated operators, and A and B big. So it's quite messy in fact here. I mean, there's more messy propagators, but this is really general because one can apply all your known theories to this. Okay, for instance, have a look at the f of r metric. So it's very simple. Okay, so you have all the formula, all the formalism already worked out. You see that there's an additional mode to the GR propagator. Okay, the extra degree of freedom, which was to be expected as you had the tuition with okay, and the mass of the scaleron is this thing over here. It must be positive to give it a stable solution. Otherwise, a tachyonic mass spoils the stability around the cosmic space, and that's really important, right? Okay, pure metric-Palatini. Okay, so just to remind you, it's when the Brownian equilibrium is equal to -3/2, right? And of course, applying the previous formalism is really straightforward, and you see, as it's also intuitive, okay? You see that the propagator is exactly what you would expect in GR, in flat curve spacetime. Flat spacetime, right? Which is to be expected. And as Jose mentioned, and which I didn't realize back then, the same thing applies to the hybrid metric-Palatini formalism that we consider R plus f of R. Okay? So there's no extra modes. If you want extra modes, you have to go into those hybrid contractions that will give you the massive modes, and we haven't gone into that yet, and probably ghost modes which appear, for instance, in f of R. So thank you very much, Jose. All right. So I don't know if I have time.
Yeah.
Okay. So yes, on Wednesday, I was thinking about, this wasn't supposed to be so it's very messy, okay? I just edited this up last night, okay? So I had other stuff which I put away. But what about dark matter? Okay. So we've had, this has also been analyzed. The hybrid metric-Palatini theory has been analyzed, has been used to mimic dark matter. We found solutions. We found solutions that they give you flat curves very nicely, so it works there. It's very similar. The approach is very similar to what was done by Salvatore Capozziello 12 years ago. We also had that in the paper. So it's So it's very similar. But I would like to show you how to use the generalized virial theorem. Okay, so it's very simple, in fact. Just algebraic. You have to define some new quantities, okay, geometric quantities, because obviously you have extra geometric terms that appear. Whoops. So that's what gives you the missing mass, right? All right. So there's two ways to determine the total mass of a cluster of galaxies. Okay. And first of all, you can take into account the dynamical motion of the member galaxies of the cluster, and with the application of the virial theorem, you can obtain an estimate for the virial mass, okay, of the cluster. Or you can take, second method is determine the total baryonic mass by adding the mass of each individual galaxy member of a cluster, okay. And taking this into account, you see that there's a big discrepancy of about 20 to 30. That's the so-called missing mass problem, right? Here we are. Okay, so let's build a model. So let's consider a self-gravitating system of identical collisionless point particles in random motion. Right? That's what is done in GR using the relativistic Boltzmann equation. Right? Okay, so of course we use the hybrid theory. In this case, it's a representation because it's much more simpler. Also, for simplicity, consider a spherical symmetric cluster. Okay, here we have the metric functions. The galaxies in the clusters are considered identical and collisionless point particles. Okay, at these scales, right? And the space-time distribution is given by the distribution function, okay, which is the FB. And its evolution is given precisely by the relativistic Boltzmann equation. You have to solve it. It's very messy. So, okay, here we are. This is the equation. The P is the full momentum. Here we have the Aristotle symbols. And, okay, let's go ahead. You just consider an energy momentum tensor of matter given by equation 39. Okay, so M is the mass. This is the full velocity of the galaxy. Here we have the du is the invariant volume element of the velocity space. Okay, so the T mu nu can be represented in terms of an effective density and of two anisotropic pressures. Okay, here we are, R and T. Rho is the mass density of the ordinary baryonic matter. So this is really standard. So it's really what is done in the virial theorem. That is that. Okay, now it's really messy, okay? So we just take into account some simplifications, right? So the field equations can be approximated into equation 41, and the relativistic Boltzmann equation finally takes this term, but also some approximations. I'll tell you exactly, more or less, which are the approximations. And also to be consistent with the local tests, and as we saw before, we see that the deviations from GR are very small, which tells you that this kind of field is very, very small, right? So the perturbations around the background field, and also the background field is very small, to be consistent with the local tests. Okay. So, similarly, we apply to test particles in stable circular motion. It also applies to galaxy clusters, right? So first of all, the metric functions are slowly varying, which tell you that the first and second derivative are very small, so we neglect all the quadratic terms. Okay, assume that the motion is non-relativistic, which gives you this condition, okay, which simplifies your field equation very much. So the gravitational field equation reduces to this here, okay, and the relativistic Boltzmann equation gives you this. So what you do is just multiply by r squared, integrate over the radius, and you get this. And the K is the total kinetic energy of the galaxies. Standard, nothing different here, except this new term. Okay? All right, so you defined the gravitational potential energy given by the standard, but you also have a different term. I mean, an additional term, which is the gravitational potential of the scalar field. Okay, so it's got a geometric origin, so we call it the geometric potential energy, right? And very similarly, we also define a new quantity, okay, called the geometric mass, because we have the scalar field, which was given by the hybrid metric-Palatini formalism in the curvature formulation, right? So you see that it's very similar to what you have in GR, but you have one extra term that comes in from the geometric effect, right? So the idea was to see if this geometric thing accounts for that mass discrepancy. If you're not following, please tell me. It might be very confusing. Just stuck in last night. Okay, so here is the familiar form for the virial theorem. Precisely what you have in GR. Okay, nothing different, but you have a new term. This thing. Right? So we define the radial, the virial radius, and also the effective geometric radius. Okay, very similarly. All right, let's go ahead. And some more definitions. So we have the virionic potential energy, given by equation 53. Taking into account the definition of the virial radius and the geometric radius. Okay, so you'll find these two quantities in terms of the virial radius and the effective geometric radius, and also the mass. Right? Okay, so and also a new definition for the virial mass in terms of the kinetic energy. And here is the final result taken from the virial theorem, right? And we know that this thing is very, very large, right? Of the order 20 to 30. But in some galaxies it gives you the order of 4, 5. So, but anyway, this can be approximated to give you this here. Give that approximation, 57. All right. So there's also a strict proportionality between the geometric mass. The virionic mass and the real mass, FGR. Okay. Okay. Now how do you apply this? First, okay. So this is the part that's that I alluded to. Now you just work out. You have to use the velocity dispersion relationships. You have to use the density distributions, and you play around with that. You can find all the quantities, all right, and you can find all the perimeters by imposing your observational tests, right? So basically, that's what we do. This is very confusing, probably. So therefore, the virial mass is given finally by this object. Okay, this approximation. And it tells you that the virial mass is proportional to the baryonic mass of the cluster and the ratio of the total mass, right? And also these geometric quantities. So the geometric radius of the cluster can be determined from observations, one the virial and the baryonic masses and the virial masses unknown. So one can play around with this. Okay, so So the idea is you have the generalized real mass. Okay? Through observations, one can take into account different quantities. All right? You define your velocity dispersion. You define your density profile, and you insert this in the equations, and it gives you constraints of the parameters. These constraints are those that we found in the weak field limit. So they're consistent. That's the bottom line. Okay. All right. So I'll just finish off. Right. So we have modified gravity, which offers an alternative explanation to the cosmological history, which is different from dark energy. Okay, so it's also fundamental what Ludwig mentioned, it's also fundamental to understand how one may differentiate these modified theories of gravity from dark energy models, for instance through nonlinear derivation, structure formation. The test from solar system, large-scale structure lensing, restrict the range of the allowed models. Okay, so surveys, these upcoming surveys will provide new opportunities to test the different cosmological models. And we do have a great wealth of high-precision observational data that will become available by these upcoming and planned surveys. And of course, we can say that we are dawning in the golden age of cosmology, which opens a window to explain the nature of dark energy, dark matter, and the nature of gravity itself. So I think it's for the young people, for the students, this is really exciting. Okay, theory, observational stuff, the synergies between it, and there's a lot of stuff that can be done. Okay, so it's really interesting. I think you guys will be the new generation and will find out, discover these solutions and answers to these mysteries. So thank you very much.
How did you define exactly the virial radius in your picture here? Because observationally, typically you define it as that radius of which density is, say, 200 times the density, etc. So is it the same?
Same way.
Actually, compare with
to define the real quantities, it's done in the typical way we do GR. Okay, same way. Okay, there's nothing different there. You take it out there, and then you just define through these constraints what are the other geometric quantities, and then you have all these parameters coming from the theory which you constrain. Okay, so that's the idea.
And also, you know that the mass to light ratio, or the virial mass in your thing, and the baryonic mass is a function of the baryonic mass, or a function of the total mass of the object. Yeah. We observe that the larger the structures, the less discrepancy you have between baryons and dark matter, and so on and so forth. So maybe I wonder if you had any idea of how the model could be, so that it gives this kind of monotonic behavior.
Yes, I don't know about that. That's, yeah, I mean, it's a few other issues. I'm not sure about
that. I just wonder, when you saw the propagation for the graviton for the Palatini case, I am wondering how would be the propagation for the R squared case?
R squared case. R squared.
Because this is a very interesting case in metric gravity.
Yes.
And according to the expression, well, probably it's a very exceptional case.
Yes, the man, he's the intuitive man. But what I think the fortunate is Lobo, right? It's, I mean, R squared is a specific case for Lobo, okay? So you should get an extra scale.
But what I'm wondering is if, because in the metric case you have that.
Oh, you mean the R squared in the Palatini?
Yeah.
R squared in the Palatini. Okay. So I didn't look that up, but you have the formulas that worked out. You just have to take into account the first derivative, second derivative, and you find the same thing.
Yeah, but in the expression that you show, you have that the propagator, it goes something as 1 over R F
you're right,
double
you're
prime.
Right.
So that is going to go to infinity.
I remember that. Okay, so right. Thank you very much for putting that out. So this precisely excludes that case. Okay.
Yeah,
you're right. Thank you very much.
That's why
so it excludes the case of you have an R Palatini squared.
Yeah.
You can do it, okay? But for this formula, we just take into account the linear stuff. Because I remember it was very nice. We have much more. But you can do it, of course. Okay. But thank you. But that formula excludes the R prime.
I think it will be interesting to see what mode it's
Yeah,
carrying
I agree
in
with
this
you, I
case,
agree
because
with
in the case of general relativity you have that R squared is renormalizable, but you have a ghost.
Yeah.
So it could be interesting how it works. in this
Absolutely
case.
right. So, I don't know, maybe you'll have ghosts, modes, maybe not. You don't think so?
I don't think you will
Well,
have any additional degree of freedom.
You don't have any additional degree of freedom.
You will not be renormalized.
But sorry, but the R squared is what you have in